Hi students, in the last lecture we have discussed about the concept of isomerism and the classification of the isomerism. So just for 2 minutes we are going to discuss what all we have discussed in the last lecture. So first of all, what are the isomers? Isomers are the compounds, they are having the same molecular formula but they differ in their physical properties as well as in their chemical properties. Such type of compounds we are called as in isomers. So again, the isomers are classified into two types. One is the structural isomer, another one is the stereoisomer. So what about the structural isomers? Structural isomers will also have the same molecular formula but they differ in the connectivity, whereas the stereoisomers will have the same molecular formula but they will have the same connectivity, but the arrangement of atom in the space will be different. So again, we have discussed about the type of structural isomers. In that, the first one is the chain isomers. What is the chain isomers? Compounds are having the same molecular formula. Molecular formula will be same but they differ in the number of carbon atoms in the chain. Those are called as the chain isomers. Second one is the positional isomers. So positional isomers are also have the same molecular formula but they differ in the position of the multiple bond, that is the double bond or the triple bond. They are called as the positional isomers. Not only the double bond as well as the position of any functional group also. The third one is functional group isomers. So what are functional group isomers? Those compounds will have the same molecular formula but they differ in the functional group. We have seen the different set of functional group isomer. The first one is an alcohol and the ether. Second one is an aldehyde and the ketone. Third one is the primary amine, secondary amine, tertiary amine. Like this, some 10 sets of functional group isomers we have discussed in the last class. The fourth one is the metamerism. Metamers or those compounds have the same molecular formula but they differ in the number of carbon atoms on either side of the functional group. Last one we have discussed is ring chain isomers. So ring chain isomer, as name itself says, in one isomer you will have the open chain, in another isomer you will have that carbon atom in the form of the ring. What we have not discussed in the last class is tautomerism. That is what we are going to discuss in this lecture. Tautomerism. So what is the tautomerism? Here first I'm going to explain based on one example called an acetone. Molecular formula of the acetone is CH3 C double bond O CH3. So here I have written an open structure of the acetone. In this open structure of the acetone, you can see a carbonyl carbon, that is this carbon, will call it as the carbonyl carbon. So carbon which directly attached to the functional group. What is the functional group here? Functional group in this molecule is ketone. What is the functional group here? Ketone is the functional group here. The carbon which directly attached to the functional group, we'll call that carbon as what? Alpha carbon. So this here you're having one carbon that is directly attached to this carbon. We can call it as an alpha carbon, as well as on the left hand side of this molecule also you're having the another carbon. So this carbon is also called as an alpha carbon. So in acetone, how many alpha carbons are there? You're having the two alpha carbon atoms. Next, in those hydrogens which present on the alpha carbon are called as an alpha hydrogens. I am again repeating, those hydrogens which present on the alpha carbon, we'll call it as an alpha hydrogen. So on this alpha carbon, how many hydrogens are there? 3. All those 3 hydrogens can consider as an alpha hydrogen. Alpha alpha alpha, as well as on left handed sided alpha carbon also is having the 3 alpha hydrogen. Total how many alpha hydrogen this molecule is having? 6 alpha hydrogen atom. So to participate in tautomerism, molecule should have at least 1 alpha hydrogen. But how many alpha hydrogens we are having? 6 alpha hydrogens. So now let us go to the mechanism of tautomerism. So what is happening here? First we'll focus on C double bond O. Already we know that the electronegativity of oxygen atom is greater than the electronegativity of the carbon. So because of this, what happened? The pi bond will polarizes towards the oxygen, and the oxygen will get the partial negative charge and carbon will get the partial positive charge. At the same time, between the alpha carbon atom and the alpha hydrogen, the electronegativity of the carbon is greater than the electronegativity of the hydrogen. So these two hydrogens which present between the alpha hydrogen and alpha carbon try to polarize towards the alpha carbon atom. So this is the alpha carbon atom, electron is polarized towards it. So alpha carbon atom will get the partial negative charge and the alpha hydrogen will get the partial positive charge. At the same time, what happened? This oxygen pick up the positively charged hydrogen atom. That is what happened here. After the transfer of alpha hydrogen on oxygen, you will get this structure. What is the difference between these two structures? In this structure, whatever the hydrogen was there on the oxygen, it was the alpha hydrogen in this structure. Okay, what newly developed here, you got the double bond between the carbonyl carbon as well as the alpha carbon. This is the newly formed double bond. Here actually you are not having the double bond in the structure. So what functional group was there in the first structure? Functional group present is ketone. So this structure I will call it as the ketoform. And what functional group was present here? You are having the double bond. If you are having the double bond, I will call it as an ene. And if you are having the alcohol, we'll call it as an ol. Combined, I will call this structure as an enol. So whenever you are having the keto form, there is a transfer of alpha hydrogen towards the oxygen and the formation of the double bond. So hydrogen will shift from the alpha carbon to the oxygen and newly one double bond will form between these two carbon atoms. This always happens in keto form. Whenever keto form is there, it try to convert to the enol. Whenever you are having the enol form, it try to convert to the keto form. So it is the dynamic nature. So keto to the enol, enol to the ketone. So both are dynamic in nature. Suppose if you are having the 100 molecules of acetone, some of them, let us 60 molecules will be in the keto form and 40 molecules will be in the enol form. So this ratio is just to explanation. I'm not saying the exact percentage of keto and enol form. So let us go to the definition of tautomerism. So what is the tautomerism? It is a phenomena in which a single compound exists in two readily interconvertible structures. What are the interconvertible structures? Interconvertible structures are keto form and enol form. So keto to the enol, enol to the ketone, they convert from one another. They differ in the relative position of at least one atomic nucleus. That atomic nucleus is hydrogen. So what is the difference between the ketone structure and enol structure? The difference is the hydrogen. In ketone structure, the hydrogen was present on the alpha carbon atom. In enol structure, that hydrogen is present on the oxygen atom. Okay, I again retain this point. So what is the tautomerism? Tautomerism is a phenomena in which a single compound exists in two readily interconvertible structures that differ in the relative position of at least one atomic nucleus. Generally it is an hydrogen. Tautomeric structures are obtained by simultaneous shift of hydrogen atom and the double bond at 1,3 position. That is why we can call this also as the 1,3 shift. What is 1,3 shift? Actually, here the hydrogen atom, I will change the color, you come to know. Here I am giving the number for the carbon atom. Here you can see the carbon, I'll give you 1, this carbon is 2, and this oxygen is 3. Actually the hydrogen is on the first carbon atom in this structure. Now after the tautomerism has happened, this hydrogen is present on the third atom. That is numbering 1 here, 2 here, 3 here. So what is happening? So first to third atom, or third to first atom, there is a shift between 1 and 3 atom. That is why we can call this as the 1,3 shift. It is further called the desmotropism. So desmos means bond, tropos means turning. So actually bonds are shifting in this tautomerism. So dynamic isomerism, why we'll call dynamic? It is a dynamic in nature. So ketone to the enol, enol to the ketone, it happens every time 24 hours in the molecule. So we can call it as the dynamic isomerism. We can call it as the cryptomerism, or allotropism, or merotropy, or keto-enol tautomerism. The regularly using name is the keto-enol tautomerism. So remember, the keto-enol tautomerism is a dynamic tautomerism. What is the difference between the resonance and tautomerism? So very important concept. So resonance is an hypothetical concept, whereas the tautomerism is a real concept. First let us explain based on the resonance. So resonance, I will take one best example where we have discussed the concept of resonance. For example, here this is the structure of the benzene. I am going to write the another structure of the benzene. This two structure of the benzene is not the real structure of the benzene. We have called this as the resonating structures or canonical structures. How many resonating structures are there for the benzene? Two resonating structures. This one, the first one, and the second one. So both are the resonating structures of the benzene. But these two structures are not the real structures of the benzene. Then what is the real structure of the benzene? So benzene is not having the triple double bonds, or it's not having the 3 single bonds. Instead of that, it is having the delocalization of the 3 triple bond in continuous molecule. So this is called as the resonance hybrid. Actual structure of the benzene is this, but what we are going to write on the paper is the first and second structure. These two are not the real structure. So what they are the hypothetical structure. Hypothetical means it is not the real. Clear? So what is the real structure? That we can't write on the paper. This is called the resonance. So resonance is hypothetical concept. So whereas the tautomerism is the real. Here we have seen the tautomerism between these two structures. If you are having the 100 molecules of a stone, some of the, for example, 16 molecule will be in the keto form and 40 molecule will be in the eno form. It is the real. It actually exists in that form. But if you are having the 100 molecules of benzene, you will have the 100 molecules of benzene only in this structure. You will not have the first structure as well as the second structure. They are the just and hypothetical concept. This is the first difference between resonance and tautomerism. So what resonance is a hypothetical concept. It is an imaginary concept, whereas the tautomerism is the real concept. Next, resonance contributing structures cannot be isolated. Isolation means it cannot be separated, whereas the tautomeric structures can be isolated. I'm going to explain again. So resonating structures cannot be isolated. Suppose if you are having the 100 molecules of the benzene, 100 molecules of the benzene will exist in this form. It doesn't exist in first and second resonating structure. If it doesn't exist, how can you going to isolate it? How can you going to separate it? But whereas the tautomeric structures can be isolated. Suppose if you are having the 100 molecules of acetone, you can separate the 60 molecules of acetone in the keto form, and you can separate the 40 molecules of acetone in enol form. There is some techniques to separate the keto form and enol form. The second point is resonance contributing structures cannot be isolated, whereas the tautomeric structures can be isolated. They can be separated. Resonating structures cannot be separated, whereas the tautomeric structures can be separated. Next, resonance. In resonance, positions of atoms, nuclei are fixed, while in tautomerism there is a simultaneous shift of an hydrogen atom and the pi bond takes place at 1 3 position. So what is happening here? Again I am repeating. In resonance there is the transfer of pi electron and non-bonding electron. Only pi electron and non-bonding electron will be shifted, whereas in case of tautomerism, what was shifting? Hydrogen and pi electron. There is a shift of hydrogen atom. So you can see in case of benzene, only pi electrons are moving around the benzene ring, but there is no shifting of the carbon atom or hydrogen atom. Whereas in tautomerism there is a shift of a hydrogen atom. Here let us see one example of one more tautomerism here. So this structure can participate in keto enol tautomerism. What is the functional group here? Functional group present is keto form. Here the functional group present is the keto form. Here how many alpha carbons are there? What are the alpha carbons? Carbon which directly attach to the functional group, we'll call it as an alpha carbon. So this is the functional group and this is also the functional group, and this carbon was directly attached to the functional group, so this carbon will call it as an alpha carbon, and this carbon was also directly attached to the functional group. This is also an alpha carbon, and this carbon was also directly attached to the functional group, and it is also called as an alpha carbon. So in this molecule, how many alpha carbons are there? 3 alpha carbon atoms are present. So those hydrogens which present on alpha carbon, we'll call it as the alpha hydrogen. Here on this carbon you are having the 3 alpha hydrogen, on this carbon you are having the 2 alpha hydrogen, again on this carbon you are having the 3 alpha hydrogen. Total you are having the 8 alpha hydrogen. So what is the condition for the resonance? So condition for the resonance is molecule should have at least one alpha hydrogen. If you are having the one alpha hydrogen, it can participate in tautomerism. So now I'm not going to take this 3 alpha hydrogens and this 3 alpha hydrogen. Instead of this, I'm going to take the central alpha hydrogen. Why? We can see the later. Now this 2 hydrogen is present on the alpha carbon, so this alpha, we can call this hydrogen as an alpha hydrogen. Any of this alpha hydrogen can participate in the tautomerism. Now what happens here? This alpha hydrogen will transfer from alpha carbon to an oxygen. Here pi bond will polarize towards the carbon, and here between these two you are going to get the double bond. After shifting of alpha hydrogen on the oxygen, you will get this structure. So this is the hydrogen where it was shifted from here. So this form is the ketol form, and here this form, what you'll call? We'll call it as an enol. We'll call it as an enol. Why only this central alpha carbon was participating in tautomerism? Why not the terminal carbon atoms are not participating in tautomerism? The reason is, if the central carbon hydrogen was participated in tautomerism, you will get this structure. After getting this structure, This hydrogen can participate in hydrogen bonding. Particularly, it is called as intramolecular H bonding. Intramolecular H bonding. So here you are having the hydrogen attached to the oxygen, and here you are having the oxygen. So between this oxygen and this hydrogen, you will get an hydrogen bonding. What do you call this? Intramolecular hydrogen bonding. This hydrogen bonding was present inside the molecule. Because of this hydrogen bonding, what happened? You got one ring. 1, 2, 3, 4, 5, 6. You got a 6-membered ring. This is the stablest form. So now in this structure, which is the most stable? Enol form is most stable than the ketone form. Tautomeric forms have different functional group, and resonating structures have the same functional group. S. In tautomeric form, functional group itself changes. So how it changes? Ketone functional group changes to enol. Enol functional group changes to ketone. In resonating structure, there is no change in the functional group. Tautomeric forms have no effect on the bond length, while the resonance affect the bond length. So the tautomeric form will not affect the bond length, whereas the resonance will have the bond length. In this structure, you can see 1, 2, 3, 4. So between 1 and 2, you're having the double bond. Between 2 and 3, you're having the single bond. Between 3 and 4, you're having the double bond. So next resonating structure is this. I'm giving the same number 1, 2, 3. So between, if electron polarizes towards the second, it will get the positive, negative. If it polarizes 3 to 4, third will get the positive, fourth will get the negative. Between 2 and 3, you got the double bond. First carbon is having the positive charge and the fourth carbon is having the negative charge. So now between 1 and 2, what was there? You're having the single bond here. Between 2 and 3, you're having the double bond. Between 3 and 4, you're having the single bond. But actual structure, you will have the partial double bond character everywhere in the molecule. So between 1 and 2, it is not the double bond. Between 1 and 2, it's not the single bond. It is a 1.5 in between the single bond and double bond. So tautomeric forms have no effect on the bond length, while the resonance affect the bond length. Resonance structures are obtained by delocalization of resonance structures are obtained by delocalization of resonance structures are obtained by delocalization of pi and non-bonding electrons, while the tautomeric structures are obtained by delocalization of sigma and pi electrons. Effect of solvent on enol content. So now here again I'm repeating this two. This is the keto form, this is the enol form. So this enol form, if it present in the water, you're having the 15%. If enol form, if you are taking in the hexane as a solvent, you're having the 92%. So what that means, suppose if I take 100 molecules, 15 molecules will be in enol form and 85 molecules will be in a keto form. When if I take water as a solvent, suppose if I take hexane as a solvent, out of 100 molecule, 92 molecule exist in enol form and 8 molecule will exist in a keto form. The percentage of enol and the keto form varies with respect to the solvent. Here when I am using the water as a solvent, 15% for the enol and 85% for the ketone. If I use hexane as a solvent, 92% exist, 92% for the enol, 8% for the ketone. So what happens for the enol form in the water? Whenever you are taking the water as a solvent, what water will do? So water forms the hydrogen bonding with C double bond O of the keto form, thereby inhibiting the intramolecular hydrogen bonding of the enol form. So if this hydrogen is transferred to this oxygen, then only keto form will convert to the enol form. But whenever you are taking the water as a solvent, in water HOH, you are having the hydrogen attached to the oxygen. Between this hydrogen and oxygen, you will get a H bonding. Again, between this carbonyl oxygen and another hydrogen, you will have the H bonding. This carbonyl oxygen was completely blocked to convert into the enol form. So most of the structure try to be in the form of the ketone if you are taking the water as the solvent. That's what it was written here. H2O forms hydrogen bonding with C double bond O of the keto form. If H2O forms hydrogen bonding with C double bond O with keto form, hydrogen cannot transfer on the oxygen. The probability for the tautomerism will decrease. So by inhibiting the intramolecular hydrogen bonding, so hydrogen bonding will be decreased. Here you are having the intramolecular hydrogen bonding. The percentage of intramolecular hydrogen bonding will be decreased. In case of the hexane, if I take the hexane, hexane cannot participate in H bonding. Why? Because it is a non-polar solvent. If I am using the non-polar solvent, this non-polar solvent cannot form hydrogen bonding with C double bond O. If it cannot form hydrogen bonding with C double bond O, the probability for the tautomerism increases. In that case, enol form is more stable than the keto form. Why? Because in case of enol form, you are having the intramolecular hydrogen bonding if I am using the non-polar solvent. But in case of keto form, you will not have any hydrogen bonding. So therefore, enol content increases in non-polar aprotic solvent like benzene and hexane. So what is aprotic solvent? Aprotic solvents are those where hydrogen was attached to any non-electronegative atom like carbon, and it decreases in polar protic solvent. Polar protic solvent, hydrogen was attached to any electronegative atom like oxygen, fluorine, chlorine. These are called as an polar protic solvent. So percentage of enol will be more in hexane, next was in benzene, acetone, methanol and water. So water is polar protic, methanol is polar protic, acetone is polar aprotic, benzene is non-polar, hexane is also non-polar. The enol content is more volatile and separated by fractional distillation. Very, very important point. How we are going to separate the keto form and enol form? In enol form, you are having the intramolecular hydrogen bonding. So because of intramolecular hydrogen bonding, what happened? Boiling point will be decreased. Boiling point will be decreased. So if boiling point was decreased, when you're boiling the mixture of keto and enol, which will come out first? Enol will come out first. So after that, ketone will come out first. So between keto form and the enol form, which is volatile? Enol form is more volatile than the keto form. So reason is in enol form you are having the intramolecular hydrogen bonding. Intramolecular hydrogen bonding decreases the boiling point of that structure. Next, so conditions for enol formation, as already discussed. What is the condition for keto enol formation? That molecule should have at least one alpha hydrogen. What is an alpha hydrogen? The alpha hydrogen is that hydrogen which present on alpha carbon. What is the alpha carbon? That carbon which directly attached to the functional group. So let us see some examples where enol formation will happen or not. For example, in case of acetophenone, what is the functional group? Functional group carbon is this carbon. functional group attached carbon we'll call the alpha carbon. So here you're having one alpha carbon and this is also an alpha carbon. So on this alpha carbon you're having the hydrogen. How many hydrogens? 3 are there. Those 3 we'll call it as the alpha hydrogen. So on this side you're having the 3 alpha hydrogen, but here you're not having any hydrogen on this carbon. Why? Because already carbon was attached to 4 bond. So here you're having the 0 alpha. At least one should be there. Here you're having the 3. So it can participate in keto-enol tautomerism. Second structure, benzaldehyde. What is the functional group carbon? This carbon is the functional group carbon. Carbon which directly attaches to the functional group, we'll call it as an alpha carbon. On right hand side of this molecule you're not having any carbon, so here no alpha carbon was present. But on the left hand side here carbon was there. This we'll call it as an alpha carbon. On this alpha carbon there is no alpha hydrogen. This molecule is having 0 alpha hydrogen. If there is no alpha hydrogen, this cannot participate in keto-enol tautomerism. So remember, benzaldehyde molecule cannot participate in keto-enol tautomerism. Third example is benzophenone or diphenyl methanone. Here also functional group is this carbon which directly attached to the functional group is an alpha carbon. Right hand side you are having one alpha carbon, left hand side also you are having the alpha carbon, but on this alpha carbon there is no hydrogen was present. Again on this alpha carbon also no hydrogen was present. Total number of alpha hydrogens on these molecules are 0 alpha hydrogens. If there is no alpha hydrogens, this molecule cannot participate in hydrogen bonding. The fourth structure is butanone. What is the functional group carbon? This is the functional group carbon. Carbon which directly attached to the functional group is an alpha carbon. Here this is the alpha carbon and here alpha carbon. So on this alpha carbon 3 alpha hydrogens, on this alpha carbon 2 alpha hydrogens. So total how many alpha hydrogens? 5 alpha hydrogens was present. For us at least one is enough. So butane 2-one can participate in enol formation. Propanol. What is the functional group here? Functional group is ketone. Functional group attached carbon is an alpha carbon. On left hand side you are having one carbon here, so this is the alpha carbon, but right hand side you are not having any alpha carbon. Hydrogens present on alpha carbon is alpha hydrogen. How many alpha hydrogens are present here? 2 alpha hydrogens are present. For us at least one alpha hydrogen is enough, so propanol can participate in enol formation. Next, 2,2,4,4 tetramethyl pentane 3-one. What is the functional group here? Functional group is the ketone. What is the alpha carbon? Functional group attached carbon. Right hand side you are having one alpha carbon, left hand side you are having one alpha carbon, but on this alpha carbon you are not having any hydrogen. You are having the 3-methyl group. So this side alpha carbon was present but 0 alpha hydrogens. But here on this side also alpha carbon was present, but instead of hydrogen what was there? 3-methyl group. Here also you are having 0 alpha hydrogen. So this molecule is not having any alpha hydrogen, so it cannot participate in hydrogen bonding. So these are some examples, okay, but we can look at any example based on this concept that condition is molecule should have at least one alpha hydrogens. Okay, so these are the homework questions today. Just try to solve these questions. If any doubt you can comment, you can call and ask. So write the more stable tautomeric structures. First one is the for phenol, methyl 3-oxobutanoate, cyclohexane 3-one, butane 2-one, 1-phenyl butane 2-one, 2-bicyclo 4,1-heptane 2-one, and the last reaction is glycerol. On reaction with P2O5 you will get one compound A. It will participate in keto-enol tautomerism and you will get the compound C. So what is the compound? A and C.